Hi, I'm Laurent Pueyo. I'm an astronomer at the Space Telescope Science Institute. You've just heard about how to build coronagraphs, and now I'm going to tell you what we can do with them. In the early 80s, we didn't know about any exoplanets, and coronagraphs were being used to look on the sun's corona. But by the mid-80s, people started putting these black occulting spots in front of stars to see what was going on around the star. And in the image you're seeing here, it's an image from a 2.5 meter telescope from the ground, where you see the black dot in the middle, the star is blocked, and you see this beautiful amount of dust that's kind of surrounding the star. That's one of the first coronagraphic images ever took, and what you're seeing here is dust that's left over from a planetary formation mechanism. No planet was seen there, but there was kind of an idea that there might be a planet around this star, and this star is very famous. It's called Beta Pictoris b. Pretty much every time over the next 20 years after 1984, that every time somebody was trying to use a coronagraph, the first star they looked at was this star, Beta Pictoris b, because everybody thought there would be a planet. So move forward, 1997, a coronagraph is added on the 3.6 meter telescope at La Silla. This time around, you're using some kind of clever optics to correct a little bit for the atmosphere in between the telescope and the star, to correct for the Earth atmosphere. And you see a little crisper image of this disk, where the disk is a little bit warped. And so now you start thinking, well, there might be a planet there. Move forward to 2008, where you're using this time the 8 meter telescope at Cerro Paranal at VLT. And this time around, that's it. We've caught it. We've seen the exoplanet around the star. Now, let's talk about the present. What we're doing now is extremely precise measurements of the properties of these exoplanets that we're finding. To do that, we're still using 8 meter telescopes on the ground. The example is taken from the Gemini telescope in Chile. This time, we've added to the telescope a very specific coronagraph that's been tailored to just find and characterize these faint exoplanets close to the star. What I showed you before was instruments that could do a bunch of things and planets among those capabilities. This time around, it's just for planets. So what you're seeing now on this movie here is the same planet, Beta Pictoris b. And now you're seeing it moving around the star. And you actually see on this movie that it's moving in close to the star. We've actually determined, based on a highly precise measurement of the orbit, that the planet is going to get really, really close to the star this summer. Pretty much, it's kind of serendipitous, but around the time that the eclipse is going to happen on Earth, this planet will be in front, eclipsing the star. Now, we've actually been able to measure it to a precision that we can predict that it's not going to be exactly in front of the star, but if it has moons, we'll see the moons passing in front of the star. And hundreds of astronomers around the world are actually trying to set up experiments now to try to catch this very unique event that, if it happens, only happens every 20 years. So now let's move forward and try to move to the future. But before moving to the future, I want to show you this movie of this planetary system with 4 planets orbiting the star. And as you can see, the planet's orbiting, and we can start thinking about whether or not they're interacting with each other gravitationally. Hubble didn't have coronagraphs when it was launched, because Hubble was launched in the 1990s, and first exoplanet was found in 1995. After 1995, servicing mission 2, 1997, people started putting coronagraphs in the new instrument that were being shipped to Hubble with the space shuttle. So this is an image of the same multiple planetary system taken by Hubble with the Hubble coronagraph in 1998. You can see that there's a bunch of artifacts that are thrown all over the place. This is light from the star that's being bounced off the imperfection of the optics of Hubble's. So there is a coronagraph in this image. Like, the star is gone, but still those little specks of light are still hitting the camera and preventing us from seeing the planets. My colleague Remy Soumer applied advanced data analysis methods, and sure enough, he was able to reveal those planets that had been observed in 1998. So that's kind of where Hubble is at, and we're working on projects trying to find more of these quote-unquote serendipitous planets in the Hubble archive. After Hubble, what's going to happen? in 2018, we're launching the James Webb Space Telescope. Now, the James Webb Space Telescope is a bunch of hexagonal pieces of glass put together. And back in the early 2000s, when people were thinking about putting coronagraphs on James Webb, the theory and the technology was not completely ready to make groundbreaking coronagraphs that, say, could be able to find an Earth-like planet with James Webb. We just didn't know how to do it back when. Instead, what we've done with Webb for coronagraphy is to operate in a wavelength regime that's very complementary to what we can do from the ground. Webb is in space and is going to be able to access wavelengths that nobody would ever be able to dream of getting from the ground. I mean, for some of the objects we're going to be looking at Webb, probably from the ground you can look at the 2-3 brightest ones and then you're done. So what's happening after Webb? Well, after Webb, in the mid-2020s, we're going to launch the WFIRST Space Telescope. WFIRST is a 2.4-meter telescope, just like Hubble, but it has two things that Hubble doesn't have. First, it has a camera with a very wide field of view, about 100 times wider than Hubble. What you can do with this is two really cool physics experiments. The first one is you can take images of a lot of galaxies at the same time, and using those, you can constrain the early universe and do some very interesting cosmological science. The second thing you can do with that is that you can look at a bunch of stars at the same time and try to see if there's a planetary system that gets in front of them and if their brightness gets enhanced according to Einstein's general relativity theory that Bonnie told you about. And using that, you can find a lot of extrasolar planetary systems. Now, the second piece of WFIRST goes in the complete opposite direction. It's a very tiny field of view camera that instead of looking at galaxy or thousands of star scales, just looks at one star very precisely. And it blocks that star using a coronagraph, and it tries to image planets around that star. In the picture you're seeing now, you're seeing a simulated image from WFIRST, where on the right you have a Jupiter at about 2 astronomical units from the star. The star is blocked by the coronagraph. And that Jupiter is shepherding dust clumps around the star. Now, what's missing from this picture? What's missing is an Earth-like planet. And Earth-like planets might be really hard to do with WFIRST. WFIRST is going to teach us a lot about how to do exo-Earth imaging in space, but it might not quite get there. Because what you really want, you want an experiment that doesn't just catch one exo-Earth, you want to catch tens or even hundreds of them, and you want to be able to study the prevalence of molecules like oxygen or water or things like ammonia or methane. In order to do that, you need a big telescope in space. You need something of the scale of like 10, 15 meters. And this is a project we're actually also working on here. It's the LUVOIR project that's going to be studied in the 2020s and hopefully launch in the 2030s. As you can see, it's a giant segmented telescope. This is a 15-meter telescope. But this time, the little hexagons, we've learned how to deal with them, and we think we can make a very precise coronagraph to be able to see an Earth-like system. That's the picture you're seeing right now. You have the star that's being hidden by the coronagraph, and in the outskirts you have a Jupiter. Then you have Earth-like planet and the Venus. And all around Earth and Venus you have the zodiacal dust that you also see with such a telescope. Now this is a big step forward in terms of what we were doing in the 1980s, when we were pretty much putting a piece of tape in front of a star in some random telescope in Chile. Now, we really think that we've learned so much that we can put all of this together, send a 15-meter telescope in space, and be able to image Earth 2.0. And I really believe that this is going to happen within our lifetimes, and we're going to get to witness that.
Well, we hope that you really enjoyed that special edition of our Eclipse webcast to show how helpful this kind of a natural event can really be, to the point that we try to recreate it manually. As always, you can get in touch with us by posting comments below on the YouTube page. You can get us on Twitter at @NatSolarObs or on Facebook at www.facebook.com/National Solar Observatory. Or you can follow us on Instagram. Our handle is @National Solar Observatory. We'd love to hear any questions or comments you might have about the webcast, anything else that you'd like us to cover in the run-up to the solar eclipse, and we hope to see you again next month.